Hello to everybody, I am Simone Nappi from University of Rome Tor Vergata, and today I'm going to present my work about stretchable wireless sensor skin for the surface monitoring of soft objects. Well, elastomers are currently used in a wide range of applications where reliability in long-term services in harsh environments is required. These materials are usually involved in aviation and automotive industries, including civil buildings, infrastructures, or medical industry. In any scenario, they can suffer from non-negligible stress factors, such as mechanical, thermal, or chemical stress that could compromise the object integrity with catastrophic results. So, early detection of signs of aging may enable a predictive maintenance to extend the life of the object and avoid severe failure. One of the major urgent symptoms of the material is the generation of cracks. These microscopic damages are due to the massive breakage in the polymer chain that makes the object brittle and therefore much more susceptible to fractures. Accordingly, irregular and awfully automatic monitoring of the object's surface integrity could extend its lifetime, preventing unexpected faults. Currently, there are several crack detection techniques based on non-destructive methods. They go from the visual inspection to a very high resolution, such as X-ray microtomography or scanning electron microscopy. Other techniques are acoustic wave based with a low to medium resolution. And finally, there are some cracks detection methods based on electric impedance and thermography. However, all these techniques usually require cumbersome measurement instruments and, in some cases, a highly trained operator to collect and parse data. So, applying these crack detection techniques over a large scale is practically not straightforward. So the goal of my work is to develop a non-invasive and early failure detection for stretchable objects by means of RFID technology. So the method is based on a conductive electronic skin enveloping the object like a tattoo that has the advantage to be easily tunable in size and density in order to monitor large area with the requested space sensitivity. The alteration of such skin due to the aging of the surface can be identified from remote by using conventional RFID equipment. Now, after a brief overview, I can show you my work. So, in the first part, I will show you space filling curves as crack detector. Then, after an electromagnetic analysis, I will show you the first crack detector object, sensor, let's say, printed on a stretchable surface. Let's consider an RFID UHF IC equipped with two ports, the RF for the communication and the anti-tamper port. Now, let's suppose to print by a conductive material an electrode over the surface we would like to monitor. Well, the idea relies on a thread connected to the anti-tamper port of an UHF RFID tag that, once damaged in some points, will set the tampering bit in the tag response. This change of status can be accordingly read from remote by conventional readers, since the IC sends back its ID and the anti-tamper status flag. But let's suppose to have a crack just in the middle of our electrode. In this case, it's impossible to detect it unless we have another shape of the electrode. So in this case, we have a kind of problem related to the coverage area from the electrode. So we need something that is similar to a nervous system. So the coverage area can be fully extended by a curve that maps a multidimensional space, even a volume, into a one-dimensional domain using space-filling curves. Originally, they were introduced by the mathematician Giuseppe Peano. A space-filling curve acts like a thread that passes through portions of the space so that every point is visited once. Moreover, a space-filling curve does not self-intersect, and it can be used as an electric closed path. Finally, the curves are self-similar. That means that it is possible to control the filling density on the thread through the selection of the curve order. The red segment denotes the longest segment that can be placed within the thread without touching it. These parameters, as shown later on, can be analytically linked to the particular curve and describes the space sensitivity of the space-filling curve as crack detector. So, a space-filling curve is univocally described in terms of initiator and generator. The initiator is the starting path that coincides with the distance between the start and end point of the curve. Each space-filling curve is moreover singled out by the scaling factor S and the iteration order. Now, let's consider the curve, and we can say that the curve can be inscribed into a regular hexagon enveloping the space-filling cell. It's easily verified that the side R of the hexagon can be linked to the initiator by the relationship reported here. Well, the space-filling curve can be mapped onto an equilateral triangular grid, so the space sensitivity of the curve can be derived in terms of the maximum number of contiguous triangles that are not intercepted by the defect. The space sensitivity can be written as indicated in the formula here. So any cracks longer than S will then surely cause the interruption of the curve, and it will be accordingly detected by the anti-tamper facility of the RFID chip. The length of the overall contour is, moreover, the sum of the all segments of the curve, and it could be expressed like the relationship reported here. So, with this relationship, we can also have an estimation of the cost of the sensor. So, for the sake of simplicity, in the previous equation we had the worst case due to the strong hypothesis made for defining it. The reported space sensitivity considers only for segments that are long enough to break the space-filling curve without considering the random occurrence. So this problem can be addressed by applying the same hypothesis of Buffon's needle problem. So we are interested in the definition of probability that an arbitrary length crack occurring in a random portion of the surface is detected by the space-filling curve. So let's consider the Vergata curve and P, namely the probability that a length-defined segment lies across the curve. In view of that, P allows only two values, 1 if the segment lies across the curve, or 0 in case of that such event does not happen. Choosing a wide population of segments having different length in the following range, so it's possible to get the probability of detection of the related curve. So, as expected, increasing in the iteration order of the curve n, thus the space-filling density, it allows higher probability of detection of an arbitrary length crack. For instance, assuming the occurrence of a half crack length, the probability to be detected goes from 75 to 90%, passing from the order 1 to the order 2 of the same curve. So the curve possesses also the surface tessellation feature, so that several cells can be placed one close to another in order to widen the area to be monitored. In this case, we have a fine localization of the crack over a larger area. So now I've shown you the capabilities of this approach for the early detection of cracks. Let's talk now about the integration of this method into a stretchable surface. The big issue here might be the cohabitation of the antenna and the crack sensor with a stretchable object. So, for instance, let's select the Vergata 2 curve of first order, and let's choose a tile of a 20.5 mm radius. Here I reported the crack detection probability for this configuration. So let's add a stretching element here that gives to the curve the stretching capability, and let's join all together. So the first thing that we can see is that the curve overall length it's almost 3 times in respect with the starting length. But we have some advantages. In fact, if we take the Montecarlo analysis, if we consider the modify the stretchable curve, we have an increment of probability of detection for cracks that are less than half length in respect of the normalized crack length. So, the magnetic element is a dipole antenna that can be tuned by 2 inductors. The electromagnetic analysis has been done considering the free space conditions. So, the current is spread all over the structure due to the massive presence of metal. Moreover, the presence of a serpentine shape generates area where the current is in phase opposition. So this behavior affects the realized gain of the antenna. Anyway, the presence of the tuning inductors allows us to tune the antenna and maximize its performance in the RFID band. So here is a reported estimated reading distance considering 3.28 watt-amp. For the whole RFID band, American or European, we have an estimated reading distance that is around 1 meter. This is fully compliant, for example, in a non-collaborative scenario for enabling a predictive maintenance service. So, the whole structure, namely the gold trace and the EcoFlex substrate, has been stretched on the x-axis up to 35% of its original shape. Then a single shell of serpentine trace is chosen for another finite element analysis. Similar to the larger system, the maximum strain in the EcoFlex elastomeric layer of the smaller system usually exists at the location where the gap opening between the serpentine traces is limited, here reported as red spots. So, the fabrication of the space filling curve began with the spin casting of PMMA, a sacrificial layer, on a 10 cm silicon wafer, followed by the spin casting of a layer of polyimide. Then, by electron beam deposition and photolithography, the gold traces have been patterned as thin film with the desired geometry. A second layer of polyimide, spin casted and cured, has been added to completely encapsulate the space filling curve. Afterwards, the sample has been immersed in the acetone for 40 minutes to remove the PMMA, and then the remaining part has been transferred to a cellulose-based water-soluble tape. Finally, using water to dissolve the water-soluble tape, the device has been moved over the EcoFlex substrate previously treated and prepared. Here is reported the prototype. Starting from the relaxed to the stretched condition, the device seems following the deformation without failures, as shown in the short video clip. So, in conclusion, we can say that an anti-tamper tag coupled with space filling curve are suitable to detect early generation of cracks. Here it has been applied to an elastomer-based object, and a theoretical reading distance up to 1 meter has been achieved. So this is suitable for handheld devices, so non-collaborative, or door-embedded devices, perhaps non-collaborative scenarios. As future development, we are going to testing the device and to perform a feasibility study for the application of real stretchable objects such as breast implants, O-ring seals, and so on. Thank you for paying attention.